Hey, welcome back to Computer Science Theory. This is COMS W3261, offered summer 2021 at Columbia University. And this is Lecture 8, Part 2, where we finally get to talk about Turing machines. So, as you'll see over the next couple of lectures, these are the greatest automata ever invented. This is the pinnacle, the peak of the art. And if you can understand this and generally what they do, you'll understand just about all of computer science. Of course, there's a lot to learn. But we'll see how we can go from simple automata descriptions gradually up the hierarchy of description to talking about machines that can do almost anything we can imagine a computer doing. So that's where we're heading. Brief historical note. What are these machines named after? They're named after a dude named Alan Turing, lived from 1912 to 1954. He was a British computer scientist who, among other things, invented the Turing machine. He also invented something else named after him that you may have heard of. He invented what's called the Turing Test. So he did this in a paper where he proposed that a good test for can a machine think is whether or not it can convince a human interlocutor that it is human. So the Turing test involves a machine communicating with some other person. The person's job is to figure out, is this a machine or is this a person I'm talking to? If the machine can convince you most of the time, if it can convince you that it has sensations, can make mistakes, can talk theology, can do all of those things, then at least for all of our purposes, it's human. You'll also see kind of crackpot headlines every once in a while claiming that some machine has passed the Turing test. In terms of meeting strict standards for passing as a human, this still seems like it's a way a ways. But you never know. He also built a sort of computer during World War II. This computer was called the Colossus, and he used it to crack what was called the Enigma Cipher. So this is a relatively famous story that we alluded to. It's captured in the movie The Imitation Game. The idea was that the Enigma Cipher was an electronic machine that would take written text and cipher it. So scramble the letters, replace letters with other letters, and send it out in code. And among other things, he worked with a team of cryptologists to reverse engineer this code and used a computer to check many possible decryptions very quickly. So this particular machine gave birth to a lot of the other arguably first early computers. So tons of fascinating history here around this guy and around the people he worked with. Unfortunately, the British government more or less hounded him to death near the end of his life. That's another sad story you can look up. But we'll move on to talking about one of his contributions, the Turing machine. The Turing machine is an automaton that can read and write on an infinite memory tape. So can the pushdown automaton. But unlike the pushdown automaton, the Turing machine has the advantage that it's essentially random access memory. It can move back and forth on this tape. It can look at whatever cell it wants. It can read that cell. It can write something else into the cell. The pushdown automaton has very limited access to its stack. It can only pop things off the top. And once things are popped, they're effectively forgotten. A Turing machine can write down notes. It can shuttle back and forth. It can keep track of multiple computations. So this infinite random access memory is going to turn out to be the final component that takes our automata over the hump from being interesting little intellectual diversions to being truly powerful, like scary powerful computers. So to draw a picture of this, earlier we drew a picture of an NFA DFA. We had state control reading in input. And then the push-down automaton looked like this, except in addition to reading in the input, it also had access to whatever was on the top of the stack. It could push and pop from that stack. The diagram of what a Turing machine looks like, we'll call them TMs pretty often, looks very similar to the NFA DFA. Except we'll call the input tape, in addition to the input, the work tape. So the distinction between an NFA and a DFA is that whereas an NFA can only move from left to right and can't modify what's on the tape, the Turing machine can move backwards and forwards. It can read the input multiple times. It can write new things down. It can replace inputs. And that's where the power is going to come from. So at every step of computation, we'll do two things. So if we're breaking down this movement into a single step that we can repeat over and over, a single round, the round will consist of two steps. We will read a symbol off the current tape square, and we will enter a new internal state. So remember, states, as we've been talking about them before, these internal states, these queues, are located inside the black box in these pictures. So we'll enter a new internal state. We may write something new on the tape. And move either to the right one square or to the left one square. So, of course, we can do this over and over, which will let us read and write arbitrarily. And we will call this piece, the part that points at one input tape square, we'll call this the head of the Turing machine. So whereas before we just talked about our current place on the input string, now we'll refer to this part of the machine as the head or the tape head. So let's do the formal definition. It's actually, if anything, it's less intimidating than the definition of a PDA, but it'll look similar. So here's our formal definition of a Turing machine. A Turing machine is a 7-tuple that is Q, sigma, gamma, delta, Q0, Q start, and Q accept. So already you should be thinking, okay, well, we don't have a set of accept states. We just have one accept state. I'm sorry, I wrote Q start and Q accept. But I've already got a start state. I labeled it Q0. So we need a reject state. That's what we need. We only have one reject state and one accept state. So that's interesting. We're used to having more than one of each of these. And we have a start state that we'll call Q0. And these things are defined as follows. Well, Q, as always, is a finite set of states. Sigma is the input alphabet. So this determines what is initially written on the tape as input. Gamma is what's called the tape alphabet. So these are things that the machine can write on the tape. And in particular, we specify two conditions on the tape alphabet. So first, we have a blank symbol. This is not an empty string. This indicates that some square of the tape is left blank. And we'll consider the whole tape to be filled with blanks, except for the input when we start the computation. And after that, the machine, if it wants to, can write more blanks. It can replace symbols with blanks. We'll also specify that the input alphabet is a subset of the tape alphabet. Of course, this makes sense because we start with the input written on the tape. And we want our TM to be able to rewrite the input. So this is a fairly loose restriction. Our delta, as always, is our transition function. And our transition function will be deterministic, at least for now, with the Turing machine. So no worrying about power sets here. It says, give me a state and give me some tape alphabet symbol that I'm reading in from my current position of the head. And I will tell you what internal state to go to, what symbol to write down onto the tape, and whether to move left or move right. And I will annotate this because this is the first time we've seen it. In some state, read some symbol off the current tape square. And then go to a state, write some symbol on current square, and then finally move left or right. And then finally we have Q0, Q accept, and Q reject. R start, accept, and reject states. So we've written down how a TM computes informally. Now we just need to write it down formally in terms of our new definition. So how a TM computes. Well, first, we begin with an input string. W equals W1, W2, dot, 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 to Wn in over the input alphabet, written on the leftmost n squares of the tape. So although our tape is infinite, we imagine it's finite on the left end and it goes off infinitely to the right. Turns out this requirement is not strict. We can relax it if we want to. But for now, we'll imagine the input written on the leftmost n squares. And we'll start pointing at, we'll say the head starts pointing at square one. The leftmost square. And of course, our start state, our internal state, that is Q0. And then 3, computation proceeds according to the transition function. other words, once we have set up our machine, we are off to the races. At any point, we are in some state looking at some symbol. That will tell us which new state to go to, what to write down on the tape, and then finally which direction to move, left or right. And then I'll add a little addendum just to make this complete. If we attempt to move left from the leftmost tape square, we do not move. So that rules out, I think, our only undefined possibility is what if we're on the leftmost square and we try to move left? We don't move left, we just stay put in that particular case. And then finally, how does this computation end? Well, computation continues until we reach Q accept or Q reject. At which point we immediately accept, reject. So this is an important thing to note because this is different from the automata we've seen before. Previously, we just kept moving around until we had read all of the input, right? We read all the input and then we'd look down and say, hey, is this state we're standing in an accept state or a reject state? In this case, all of our states are just sort of intermediate states. And as soon as we hit the accept state, we stop everything and say, okay, we're done, we accept. Similarly, if we hit the reject state, stop everything and reject. And I want to add a note. This means we don't necessarily stop. In particular, we might loop. We might have some automaton that never reaches Q accept or Q reject. And if you think about it, the only reason we knew we would always accept or reject previously with a push-down automaton with an NFA or a DFA was that we read in an input symbol every single step, and our input was finite. So we knew in a finite number of steps, all the branches would die, would end, we would accept or reject. Here, we might have this strange looping property. We might go around in circles forever without accepting or rejecting. That's new, and that's an eventuality we're going to have to talk more about as we think more about Turing machines. Another note, and I'm still going to add more notes after this video wraps, but I think these notes are important enough that we should write them down, which is TMs are often too cumbersome to write out formally. In other words, we're reaching the point where our automata are very, very powerful, and we'll be able to write out state diagrams for Turing machines, and we'll be able to write them out formally, and we'll do that a little bit, but very quickly we're going to get to the point where we realize these things can do a lot. We'll start writing down, instead of formal descriptions, what we call implementation descriptions, which is where we just describe how the tape head moves around without formally specifying every transition. And eventually we'll even get to high-level descriptions where we are so confident in what our TMs can do, we just throw all the details out the window and write down precisely specified algorithms. But I'm getting ahead of myself. For now, keep thinking formally. In particular, there's another formal notion that'll be helpful to us when we talk about Turing machine computation. And that's the idea of a configuration. So a configuration of a Turing machine is really just a snapshot at any point in computation. So this is a deterministic machine. Every step it reads, writes, and moves. So at any step, you can imagine a snapshot which tells us exactly what's going on at that moment in time. That's what a configuration is. So definition, a configuration consists of a current state, the tape contents, everything that's currently on the tape, and the head location. It's pretty clear why we want to know all three of these things. If we know all three of them, then we can continue the computation. We can pick it up where we left off. These are the three things we need to do to read the tape and continue our computation. So this is often written as UQV for a tape, sorry, for a Turing machine in state Q with the string U to the left of the head and the string V to the right. And then the head is on the first symbol of V. So in other words, if I wrote 01101 Q3 1000, this corresponds to the following picture. Some Turing machine who is in state Q3, who is reading the input string, and the input string looks like 0, 1, 1, 0, 1. Didn't leave quite enough space. 1, 0, 0, 0. And then blanks all the way down to infinity. And then Q3 being before the 1, 0, 0, 0 tells us that it is pointing at the first symbol of that string. So a configuration fully captures the state of the machine. So we'll also say that a configuration U, A, Q, I, B, V yields U, Q, J, A, C, V if delta of Q, I, B equals Q, J, C, L. So I've just written a bunch of symbols, so I want to make sure I gloss it for you. Essentially, this is saying we're in QI, we read B, and then the output of the transition function is saying go to QJ, write C, move left. And if we read these two configurations, we'll see that's exactly what happened. QI turned into QJ. We read in B. That was the symbol on the tape immediately to the right of QI. We wrote a C in place of a B, and then we moved left. So the character A moved from being the character to the left of the head to the character directly under the head. And similarly, if delta QI B equals QJ C R, then we have that the configuration UA QI BV yields, and I'd encourage you to pause the video at this point and see if you can write out the new configuration for yourself. In particular, remember we're in state QI, we're reading symbol B, and it's telling us to move to state QJ. It's telling us to write a C in place of the B, and then it's telling us to move to the right. So in other words, we move to the right of the C, and we are now looking at the beginning of string V. So just to be clear, A and B are in the tape alphabet, and U and V are arbitrary linked strings, and QI and QJ are states in this example. Hopefully that's clear from context. So we've just introduced some formalisms to say a configuration, that's just a snapshot of the machine. And we've introduced some formalisms to say this configuration yields the next configuration if the transition function says, go here from there. Why this is convenient is it lets us formally define Turing machine acceptance, which we always like to do. That is, this is the last part of our definition of any automaton. What precisely are the conditions that make it accept? So we've said we accept immediately if we ever reach the accept state. What reaching the accepted state looks like in terms of following the transition? Well, a TM, Turing machine M, accepts a string W if there exists a sequence of configurations C1, C2, ... CK, such that C1 is the start configuration, what's the start configuration? Well, it's exactly what we said above. It's what the tape looks like when we start. That is, we're in Q0, we're at the leftmost square, and the input string is immediately written on the tape below us. CI yields CI plus 1 for I less than K. That is, if you're in some configuration, it should take you to the next configuration in the sequence on the transition function. And CK is an accept configuration. That is, the state is Q accept. So that is our formal definition of a Turing machine. We've said, well, a Turing machine, like any automaton, it's just a 7-tuple. It's got some states, an input alphabet, and a tape alphabet. Really, you only need to think about the tape alphabet. And then our transition function works deterministically this time. It says, if you're in this state and you see this thing on the tape below you, go to a new state, write some new symbol on the current tape square, and move left or right. How a TM computes, we have some input string that's on the tape. The head starts pointing at the leftmost square. That is, it starts pointing at W1. The start state is Q0. And then we just continue. We follow the transition function over and over until we reach Q accept or until we reach Q reject, at which point we immediately stop, or maybe we loop forever. We defined a configuration and yielding configurations, but really all this did was make formal our notion that the TM continues to run until it accepts. There's actually not that much new in this page. It's just some nice formalizations. So I want to talk about two new concepts. Well, one's an old concept, recognizability. Another one is a new one, decidability. And we need to distinguish between these two things because a Turing machine works a little differently from the previous automata we've seen. So the idea behind this section is, like other automata, TMs can accept or reject. However, they might loop forever. What does it mean to recognize a language? In particular, does it mean we always accept when we see that a string in the language? Or does it mean we always accept when we see a string in the language and we always conclusively reject when we see a string that's not in the language? That's what these two concepts are going to separate. So in particular, we'll define Turing recognizability and we'll say the set of all strings a Turing machine M accepts is the language LM of M. A language is Turing recognizable if some Turing machine recognizes it. So we've done two things with this definition. We have brought back our familiar notion of recognizability. This is defined just as we've defined it previously. We've defined a set for every Turing machine. That is the set of all strings on which it accepts. And we've also created a new class of languages, the Turing recognizable languages. We're going to see that this is a bigger class than either the regular languages or the context-free languages, because Turing machines can do so much. However, we also need to define decidability to deal with this looping issue. So we'll define Turing decidability, and we'll say a language L is Turing decidable. Sometimes we'll drop the Turing part of that because we're only going to talk about decidability for Turing machines. If some Turing machine decides it, that is, it accepts on all strings in L, and it rejects on all strings not in L. A TM that always accepts or rejects is called the decider. So Turing decidability is strictly stronger than Turing recognizability. So if some Turing machine decides a language, well, it definitely recognizes the language because it accepts on all the strings in L. It also does something else. It rejects on all strings not in L. So we'll write down, note, Turing decidability implies Turing recognizability. However, it's certainly possible that we have some Turing machine that recognizes a language, but on some strings not in the language, it loops forever. And in fact, that's going to turn out to be much easier to recognize a language than to decide a language. So this distinction is going to come in crucially in the following lectures. That's decidability and recognizability. Now, let's do what I'm sure you've all been waiting for, a specific example of a Turing machine that will recognize a language. here is our example. Example, a Turing machine that recognizes, so it's got to accept on every string in this language. The language A equals 0 to 2n for some n greater than or equal to 0. So it'll recognize strings of zeros whose length is a power of 2. This is a tough language to recognize. It's not clear that we could do it with a context-free grammar. Certainly probably couldn't do it with a DFA. And we're actually going to give several descriptions of this Turing machine to show you some equivalences. So we'll start with an implementation level description. And this is what we'll frequently do with Turing machines. It'll save us some time and energy. In particular, this is a higher level description than a formal 7-tuple or state diagram. We describe how the head moves around and how it modifies the tape, but not individual states or transitions. So quickly, we're going to get to the point where we understand when an implementation level description describes some real Turing machine, and it's going to become arduous to take that implementation level description and turn it all the way into a formal 7-tuple. So after this example, we'll probably never see formal descriptions again. We'll just talk implementation level descriptions. So here's what an implementation level description of this Turing machine that recognizes this language might look like. So we'll say M2 is a machine that does the following. On an input W, first we read input left to right along the tape, and we cross off every other 0. So effectively, we divide the number of zeros by 2, right? We're crossing off every other one. 2 is our base case. If we just saw a single 0, we accept. So of course, we do want to accept a single 0 that has length 2 to the 0. If we had 2 zeros as input, or we cross off 1, and we'd have 1 0 left, we want to go back and we want to accept because it has 2 to the first power zeros. So we'll just repeat these steps. We'll say, otherwise, if the number of zeros was odd, reject. We'll say otherwise, that is, if it's not odd, if we fail step 3, because of course when we reject, our Turing machine will stop immediately, we return the head to the left end of the tape and repeat from state 1. So I claim that following these 4 steps will do precisely what we want. And this is an implementation level description, written in more or less plain English, talking about what the head does, talking about how we manage the things on the tape, but not actually writing down states or the transition function. So an example of how this Turing machine might work Well, suppose we have 16 zeros. That's step 1. We read the input left to right, and we cross off every other 0. So at that point, now we have 8 zeros. Step 2, we did not just see a single 0, so we don't do anything on step 2. The number of zeros was not odd, so we don't reject. And then we return the head to the left end of the tape and repeat from state 1. So we'll go from there, 8 zeros to 4 zeros to 2 zeros to 1 0. And then we will accept. If the length of the string of zeros is not a power of 0, a power of 2, so suppose we have 14 zeros, then we cross out every other one. We get to 7 zeros. We just read 14. That's an even number, so we'll do it again. We'll cross off every other one. We'll end up with 4 zeros on the tape. We start by crossing off the first 0. I guess we'll end up with 3 zeros in that case. But the most important part, no matter how we cross things off, is when we read through 7 zeros, we found an odd number, so we reject on step 3. And this will work for any power of 2. So this is a fully defined machine because I've made it clear what we do on every input. And now we can take this and we can make it formal. So number 2 is a formal description of M2. So this is in contrast to the implementation level description. So the formal description of M2 is just a 7-tuple. And we'll see that it'll be a little harder to understand. In this particular case, it's possible, it's doable. So we'll say M2, well, it's got to be a 7-tuple. Q, sigma, gamma, delta. We'll say Q1 is our start state. And we'll have Q accept and Q reject. Q1, Q accept, and Q reject are perfectly well defined by themselves. We will need a bunch of states, Q1, Q2, Q5. Turns out we're going to need 5 states. That's not obvious ahead of time. I just have the construction written down. We'll also need Q accept and Q reject. The input alphabet is just 0. So this is a language that's unary. All it has is zeros. So we'll only see zeros on the input tape. However, like the stack, we're going to want to write down and store things that aren't necessarily on the input alphabet. So we'll have the blank symbol, which is always required. The blank symbol starts on every square of the tape that's not the input. We'll have 0, as we've also required that the input alphabet is a subset of our tape alphabet. And then because we're going to want to cross things out, we'll add an X symbol to our tape alphabet. So we'll replace zeros with X's and we'll consider them crossed out. And the transition function will be described by a state diagram. So we've seen a lot of ways of describing transition functions formally. All of them are effectively functions. Sometimes we've described them procedurally. Sometimes we've written out every single input and output. Occasionally with pushdown automata, we've said, here's what we do on these certain inputs. And we've just categorically said on all other inputs, we go to the null state. Now we're leveling up once again. We have a transition function that is too painful to write down in full. So I'm going to describe it with a state diagram that will tell me, okay, on these states, on these inputs, move from state to state. So here is my state diagram. We know just from reading what I've written already that it ought to have 5 states plus the accept state and the reject state. So we'll begin with the start state Q1. And we'll say, okay, suppose we're in Q1 and we see a 0. That's the first thing we're going to read in. According to our sketch above, we are going to want to cross out zeros one by one all the way until we hit the right end of the tape. But I'm actually going to do something special here to start. I'm going to replace my very first 0 with a blank. And I'll annotate this. This means read in 0, right blank, move right. So we'll use our arrow notation, not unlike push down automata. We've got 2 input fields, Q1 and 0, and 2 outputs, or 3 outputs, what state we go to, what we write, and which direction do we move, left and right. So that's captured by this particular arrow. We read in a 0, we write down a blank, we move to the right. Why do we write down a blank? It's because we want to mark the leftmost end of the stack. There are other ways we could do this, but it'll be convenient to know, okay, we read a blank moving left. That means we must have got back to that first 0 that we replaced with a blank. So it's a little trick, kind of like pushing the $sign on at the beginning of the stack. Okay, so now we're in Q2. And at this point, we're kind of imagining that we're starting to move right across the string, reading in zeros and crossing them out. So we'll say if we read in a crossed out thing, well, we have nothing to do with it. It's probably happened at some previous stage of computation. So if we see a crossed out thing, we just move right and ignore it. If we read in a 0, now we are going to cross it out and move right. So we kind of imagine the first 0 is kind of still invisibly there. It'll be our base case 0. We're crossing out the second 0. And now we want to just move between a couple of states, alternately writing crosses and zeros whenever we see a 0. So we've just crossed out a 0. So the next 0 we see, we're going to move right without doing anything. Then if we see another crossed out thing, we ignore it. If we're reading in a very large input, at later stages, we might have many, many crosses. So we'll stay in Q4 for a while. The next 0 we see, we'll cross it out. And then the next 0 we see, we'll ignore it and we'll cross it out. So at this point, we're going back and forth between state Q3 and state Q4. Now, there's 2 things we want to happen when we get to the end of the zeros, based on whether we've read an even number of zeros or an odd number of zeros. So if we've read an odd number of zeros, that is 3 or more, well, we've gone from Q1 to Q2, Q2 to Q3, Q3 to Q4. That's what happens when we read 3 zeros. On the 4th 0, we go back to Q3, 5th to Q4, 6th to Q3, 7th to Q4. And we see that whenever we've read an odd number of zeros greater than our first 0, we'll be in Q4. And if at this point we reach the end of our string, well, we should immediately reject. We should say, okay, we see a blank. It's the end of our string. We see an odd number of zeros, and we have more than 1 0 on the tape. Well, we'll move to the right. Not that that really matters at any point, because we're going to the reject state. On the other hand, if we read in an even number of zeros, in which case we can see we're always in state Q3, and then we reach the end of the zeros, well, we'd like to start over. So first, we detect a blank that says, okay, we're at the end of the string. We're going to start moving left now. For a while, we're going to continue moving left. So no matter what we see, a 0 or a crossed out, we keep moving left. And now is where our blank square comes in handy. When we see our next blank square and we've been moving left for a while, we say, aha, we're at the beginning of the string, our 0 that we've replaced with a blank. We'll consider it read. We'll move to state Q2, and then we'll try to read in a second 0. Last few things to add, just bits and pieces to make sure we're completely well defined. Our Turing machine should have outgoing arrows on 0 on every member of our tape alphabet from every state, because all of these things are possible. There's no implicit branch dying here because there's no non-determinism. So we do need to fill in a few more things. First, from state Q1, well, if we start and we have a completely empty tape, or for some reason we have just an X on our tape, we're going to reject immediately because those strings are not properly formatted. We also need, let's see, Q5 has outgoing edges on 0, X, and blank. Q3 has outgoing edges on 0 and blank. Forgotten. There we go. On an X, we should stay in Q3. Q4 has outgoing edges on 0, X, and blank. And Q2, the one I've conveniently left for last, what happens if we're in Q2 and we see a blank? Well, in that case, we have our first 0, our first blank on the far end of the string, and we moved one more space to the right. We've seen another blank, which means we've read in one single 0. We've reached the end of our computation, and we accept. Now, you could certainly pause and go through that explanation a few times and try to follow everything I just said. But it's completely okay if this is your first time through and you're like, all right, I got lost in all of these transitions. The point is just that we could, if we wanted to, write this transition function down as a state diagram. And to be honest, we're never going to do it again. But I will, for the sake of completeness, give you some better intuition by following a string through this state diagram. We'll follow exactly what's going on just to see it all happen once. So here's our example. And following this example will help us watch the way this state diagram works. So imagine we have the input 0, 0, 0, 0. It's all on the tape. It's aligned with the left. And we are going to track, as our Turing machine computes, the current state and the current state of the tape, plus where the input head is. So one thing I could do here is I could just write down a configuration. That'd be one way to do this. I think it's actually easier to see if I write down the state and then draw a little picture of the tape and the head separately. But you could absolutely replace every row in this table with a configuration if you wanted to. That would be a full description of the Turing machine's computation. So we'll start at state Q1, and our tape will have 4 zeros, and I'll be drawing a little arrow to indicate where the head is pointing. So in this particular case, we start at Q1, we read in a 0, we write a blank over that 0, and we move to the right. So here, we're taking this first edge, we end up in state Q2, we write a blank, we move, so we're now looking at our second 0. From Q2, we read another 0. This time, we cross it out, and we move to the right again. So now we're in state Q3. We have blank, cross, 0, 0. We're looking at the next 0. From here, we're going to read in another 0, move to the right, but we don't rewrite anything this time. So now we're in state Q4. We have blank, X, 0, 0, we're looking at the final 0 in our input. And then from state Q4, we read in a 0, we cross it out, we move to the right. So our tape head is now looking at the blank that's off the right to the side of the input string. And we're back in state Q3. We're going to need the second line of our table. So now we're in state Q3, and we're looking at a blank. So we'll take the edge on the blank from Q3. It'll tell us don't write anything down, just move back to the left. And then we'll do these edges for a while. When we're in Q5, as long as we're seeing zeros or X's, we continue moving to the left. So we go to Q5, and our tape slash head looks like blank X, O, X. And then Q5, Q5, Q5. Each time we stay in Q5, we go around this loop and we move to the left until we are pointing at our first blank. I'm just going to write the rest of these in black. Now we are looking at a blank, so we turn around and start our second pass. We start going to the right, and we start counting and crossing out zeros again. So we go to state Q2. We move to the right. Now we're in state Q2. We see a cross, so we stay in state Q2. We're still waiting for our first 0. So Q2. Now we're at a 0, so we take the edge to Q3. We cross out the 0. From Q3, we read in the cross. We move to the right. So then Q3. And then finally, we are almost done. We now have a tape with all crosses. We're looking at the blank. The right of the tape, we see a blank from Q3. We go to Q5. Again, we go Q5 to Q5 to Q5 and find ourselves at our first blank spot representing the very first 0. And now we move to the right. We go to state Q2. From state Q2, we go Q2, Q2, Q2. We're reading in these X's until we're looking at the blank at the end of the tape string. And then finally, we see this blank, and we take the edge to Q accept. In other words, we had 1 0 left, represented by our convenient blank symbol at the beginning of the string. We moved to the far right. We saw no other zeros, so we know that we must have started with the power of 2 and whittled things all the way down. So our tape at this point, I suppose, since we've moved right twice, it doesn't really matter, but we're over here looking at the second blank, and because we've seen the accept state, we stop and immediately accept. So that is what our computation on this automaton looks like. You should be able to retrace my moves because I've essentially written down 20-odd configurations and follow the path of this deterministic automaton from Q1 all the way to Q accept on this string or another string. But this will be the only state diagram for a Turing machine we'll use because we're going to be going, switching over to more implementation level descriptions. So that is all for today for lecture 8. Next time, more stuff about Turing machines. We'll see even more crazy gadgets we can add on to Turing machines. And surprisingly, we will prove that they don't really add power. We'll say, look at this crazy gadget. What if a Turing machine had this power? I guess it's not any more powerful. So we can assume that we always have the crazy gadget without loss of generality. That'll be fun. We'll talk about decidability in the context of specific languages that are and are not decidable. We'll introduce things called enumerators that is Turing machines with attached printers. We'll see Cantor again. It's really, next lecture 9 is maybe my favorite lecture of the whole course, because we finally get to go from automata to the big picture, all the way up. Readings for today, as a reminder, it was 2.3 for the context-free pumping lemma and 3.1 for Turing machines. And of course, homework number 4 is due on Monday, 7/26, I think. And the next homework, homework 5, which has 10 extra credit points, is due next Monday, August 2nd. So thank you very much for listening. See you in the next one. Bye.